Hello again, everyone, and welcome to the next lesson in our Cosmic Adventure lecture series. My name is Dr. Valerie Rapson, Assistant Professor of Physics and Astronomy at SUNY Oneonta and past Director of the Dudley Observatory. Today we're going to talk all about the Arecibo Radio Telescope. You might know that the Arecibo telescope collapsed back in December of 2020 and is therefore no longer functional. But now that we have a better sense of exactly what happened to cause its collapse, I thought it'd be a good time to talk about the history of the telescope and some of the cool discoveries that it has made over the years. So we'll start this lesson with a brief history of how and why the telescope was built and exactly how it works. Then we'll move into some of those big discoveries, including a Nobel Prize winning discovery related to pulsars. Then we'll wrap things up by talking about the end of the telescope, the ultimate collapse, and what we have to hope for with the future of radio astronomy. Let's begin with a brief overview of the Arecibo Observatory. Arecibo was a 1,000-foot diameter radio dish that both received and transmitted radio signals, and it was located down in the island of Puerto Rico. You can see an aerial view of the telescope in the bottom right here. So the dish was about 1,000 feet diameter or 305 meters, and there were 3 towers with strong cables that held up the receiver and other scientific instruments above the radio dish. Arecibo was the largest solid single dish radio telescope in the world up until 2016 when China built the FAST radio telescope, which is about 1,600 feet in diameter. We'll talk more about that at the very end of the presentation when we look towards the future of radio astronomy. Arecibo saw first light back in 1963, and it was functional until almost 2020. And during that time frame, it conducted a great deal of science, both in the astronomy realm as well as in the Earth and atmospheric science world as well. Now, Arecibo did not actually begin as a radio telescope. It was actually originally funded by the Department of Defense and built to study Earth's ionosphere. If you take a look at the cartoon on the right here, you can see all of the different layers of Earth's atmosphere. We, of course, live down here at 0 on the surface of the Earth. All of the weather happens in the lower troposphere. And the ionosphere is a couple layers up, kind of at the base of the pink region here, near the line between the mesosphere and the thermosphere. The ionosphere, as the name suggests, is a portion of the atmosphere that is filled with ions, or atoms that have lost their electrons. As UV radiation from the sun and outer space comes into Earth's atmosphere, some of those atoms at this height will absorb that UV radiation and the electrons will get torn off. So you basically have a layer of free-floating electrons along with the nuclei, the positively charged ions that are left over. Now, Arecibo was built to study the ionosphere, and specifically, we wanted to be able to detect any nuclear warheads. Remember, this was 1963 in the midst of the space race, and Russia and other countries possibly were starting to develop their own types of missiles and warheads, and we wanted to be able to detect and protect our country if any of these warheads were headed our way. So this observatory was designed to study the ionosphere and look for any changes in the ionosphere due to the presence of an incoming warhead. So how exactly does this happen? How can Arecibo tease out information in the ionosphere just as a radio telescope? Well, the key here is that Arecibo was not just a receiver, it was also a transmitter. So let me share with you how this works. The basic idea is that you can send out a signal into the ionosphere at a very specific frequency. That radio signal will bounce back to Earth, and then you can receive it with the radio dish. And you can measure exactly how strong the signal is, as well as what frequency it comes back at. So if you take a look at the little cartoon graphs on the bottom, we show frequency on the x-axis and power, or basically strength of the signal that you receive, on the y-axis. If you send out a frequency and bounce it off the ionosphere, if the frequency is transmitted in a very narrow range, we actually expect not to receive all of that exact frequency back. We expect a frequency shift due to the motion of electrons in the ionosphere. You have electrons that are all moving around, and the electrons that are moving towards us are going to cause a slight Doppler shift in frequency towards the blue end, and those that are moving away from us are going to cause a slight Doppler shift in frequency towards the red end. And what that ultimately gives you back is a wider range of frequencies received from the original transmitted signal. And based on the width of frequencies that you receive back, you can actually convert that into a temperature and get a sense of exactly how quickly the electrons are moving in the ionosphere. From that, we might be able to detect the presence of an incoming warhead. If you have a missile traveling through the ionosphere, that is going to disrupt the ionosphere, cause changes in the motions of the electrons, and we might be able to detect that through this technique. We can also get a little bit of information, not just about the temperature and the motions of the particles, but also what they're made of as well. The right-hand graph shows a similar concept where you're again transmitting a very narrow frequency, but the information that comes back has a little bit of a different shape. You have a thin, narrow frequency range in one portion of the power spectrum, but then it also widens at the bottom here. And that width, that change, is because you have electrons that are near different types of ions. So in the top, you have electrons reflecting information that are near O+ or oxygen ions. And in the bottom, you have electrons bouncing signal back that is near a hydrogen ion. And through some complicated modeling and mathematics, you can actually use the width of the spectrum to tease out not only how quickly are the electrons moving, but also what types of ions are in the atmosphere. So we can do a lot of cool science within our own atmosphere with this telescope, and also hopefully protect our country a bit. So let me show you some pictures of the original construction of the observatory. Arecibo was actually built in the base of a natural sinkhole. You can see that in the picture on the left from 1962. So here's the base of the sinkhole. There's some vehicles and some metal down there. They're getting ready to actually build the radio dish. Here's the road that goes back up to the surface. And on the right, you have an image from 1963 where most of the telescope is built on the bottom there, and you have a person on a ladder starting to hang some of the cables that are going to help hoist that receiver and antenna above the radio dish. The construction was overseen by Cornell University, and the telescope was really spearheaded by an astronomer named William E. Gordon. He was an ionospheric scientist, so he saw the benefits of using Arecibo to do those ionospheric studies, but he also had training as an astronomer, so he saw the radio astronomy benefits as well. So this really led to a great partnership between Cornell and the Arecibo Radio Observatory. Cornell really oversaw the science that happened for many, many years after Arecibo was built. Let's take a quick look at exactly how Arecibo works, and specifically at the different parts that make up the observatory. We already saw that this is a 1,000-foot dish, but the dish is not one solid structure. It's actually made of thousands of aluminum panels that are held together by steel cables. I snagged this picture of some people walking underneath the dish from the internet, so you can see a group of people here. And if you visited Arecibo, you could walk under the sides of the dish, and you can tell that there are many individual panels here that just kind of get stitched together to become the radio dish. We also mentioned that Arecibo was embedded in the ground in this natural sinkhole, and that also means that the dish doesn't move. Most radio observatories today are much smaller, and the dishes are on some sort of device that can move and point them in different directions of the sky. But Arecibo being built literally into the ground meant that the Earth was the thing that was pointing the telescope. So you couldn't really choose where you wanted to look in the sky. You had to rely on the rotation of the Earth and some adjustments that could be made with the receivers at the top to try and study a specific portion of the sky. The image on the bottom right there is Arecibo in the early 1990s. And this looks a little bit different than some of the images we've seen so far, the aerial views at least, because the receivers are a little bit different. We're going to talk next about exactly what was up here and how those receivers and antenna have evolved over the years. So as we've seen in previous pictures, there are 3 concrete towers that have cables which support the antenna and the receiver for the telescope. You can see the original receiver that has these things called line feeds, which act like antennas to receive the signal. That's on the picture on the bottom left here. This image is from 1972. And the way this basically works is you have Arecibo, the dish at the bottom. It is a spherical dish, and the shape of the dish is very important. When we build professional telescopes, we don't make the main mirror or the optical system a spherical shape. We usually make it a parabola, a little bit more curved. And what that does is it allows all of the light that comes in and hits the primary mirror to then reflect back and all come to a focus at the same point. But Arecibo was purposefully built in a spherical shape to allow it to do a little bit of additional pointing that wasn't reliant on the motion of the Earth. So take a look at the cartoon on the right-hand side here. Here you have the main dish, the primary reflector as they call it. That's the Arecibo radio dish. And you have light or radio signals either coming in from the ionosphere or coming in from space. And if that light comes straight down, you can see that it's going to hit the radio dish. It's going to hit only a small portion of the dish, and it's going to reflect back towards the antenna, towards a focal point here. But with the shape being spherical, light that actually comes in from a slightly different position is going to end up focusing at a different point. So if you look up here, there's a faint blue oval circling around some galaxies. It's just cartoon galaxies here. And all of the light from these galaxies, that is the blue signal, which focuses at this line. And then over here, we have a slightly different set of stars and galaxies. That's the green circle. Their light comes straight down, bounces off a different portion of the dish, and ends up coming to a focus at this point. So by moving the line feeds that act as antennas, we can actually slightly adjust our pointing and look at slightly different regions of the sky by picking out light that is focusing at a different location. And this is all again because we have chosen this spherical mirror shape. We have purposefully made it so that all of the light doesn't focus at one location. It focuses at different spots so we can pick and choose where we want to observe. Now, another tricky thing with this shape dish and the type of radio light that we're looking at is that when the light reflects off of the dish, it doesn't come to a focus at a single point, but rather it comes to a focus along a line. So you can see here some of the light focuses at the very base of this black line. Some of the blue light focuses near the top. So the antennas have to be designed to be a certain specific length based on the frequency of light that you want to observe and the location of the sky that you want to observe in. So astronomers would actually have to swap out the feed lines to change the frequency of light that they wanted to observe, and they had to be designed very specifically to coincide with the shape of the mirror and the frequency of light that they were going to observe at. So all of this, while not ideal, was done purposefully to counteract some of the issues that we have in radio astronomy. But as technology improved, they actually changed the design of the receiver, and they built what's called the Gregorian dome. That's the big white dish that you see in most of the pictures of Arecibo. The Gregorian dome was added in 1997, and basically what was inside of this dome was other reflecting pieces, so basically just smaller dishes that would reflect the radio light. And it ultimately took all of the light from a specific portion of the dish and it focused it all to a single point. So you no longer had to have those long line feeds. You could just have a receiver that would gather all of the light from a single location inside the Gregorian dome. So here, if we look at the right-hand side, the cartoon kind of shows that. If we look at that blue light that was focusing in the middle of the dish again, the light, as you can tell, basically crisscrosses. It doesn't come to a focus all at the same point. But once it enters the Gregorian dome, the shape and the size of the dome are designed to reflect all of that light. So it bounces off of the secondary reflector, it hits a third tertiary reflector, and the shape and the location of those different reflectors ultimately make all of that radio light focus at a single point, which is then fed through the receiver and read out as an image. The picture on the bottom left just shows you the basic design here. The Gregorian dome can actually shift left and right. So that's how we change the position in the sky. Just like in the previous slide, how we talked about moving the line feed to different locations to pick up signal from different portions of the sky, by moving the Gregorian dome around a little bit, you again can choose where in the sky you want to gather light from and point the telescope a little bit. Now, the Gregorian dome and all of its instrumentation was quite heavy, so they had to add some additional suspension cables to keep that hoisted up there. So just keep that in mind as we talk about the ultimate demise and thinking about all of the weight that had to be supported by these metal cables. To finish up our discussion on the history and construction of Arecibo, I wanted to talk a little bit about the science behind why Arecibo is so big and how exactly it sends and receives signals. So first, why did we bother to build this humongous 1,000-foot wide radio dish? Well, large telescopes have two main benefits compared to their smaller companions. First, large telescopes can naturally collect more light over the same amount of time, and they also produce higher resolution images. So when radio signals arrive at Earth, they are often pretty faint. They may have been faint to begin with, or they traveled so far that they spread out and the signal is fairly weak. So Arecibo needs to be really large to be able to detect enough signal to actually pick up that radio detection from space. Secondly, we want to have a high resolution image. Now, normally I don't show you equations and stuff, but this is a super simple one, and it shows you the nice relationship between wavelength of light that you're observing and the diameter of your telescope. The resolution, or basically how far apart two objects need to be for you to distinguish them separately in an image, is equal to 1.22 times the wavelength of light you're looking at divided by the diameter of your telescope. If we calculate this out for Arecibo when it's observing at 1 gigahertz or 0.3 meters of wavelength, we end up with a resolution of 0.0012 radians, which is just a fraction of a circle. There's 2 pi radians and 360 degrees. Or to put it in terms of numbers that astronomers use more frequently, that's 3.4 arc minutes. So in 1 degree, there are 60 arc minutes, and in 1 arc minute, there are 60 arc seconds. If you want to compare this to the full moon is 30 arc minutes across. So this is 3.4 arc minutes resolution. So we're seeing details on scales much smaller than the width of the full moon as observed from Earth. Now, that's not bad, but the idea with resolution is you want your number to be small. The smaller your number, the closer two objects can be in the sky, and you still have the ability to distinguish them as separate objects. We can compare Arecibo's resolution to that of Hubble. Remember, Hubble is a smaller telescope. Hubble's resolution is 0.05 arc seconds, which is actually 4,000 times better than Arecibo's. Now, why is that the case? Well, remember that it's not just diameter of the telescope, it's also wavelength. Hubble observes at visible wavelengths, which are much shorter. So Hubble can have a smaller diameter, and this ratio works out to give you a smaller or a higher resolution value than Arecibo does. So radio telescopes have this trouble basically that they're observing really long wavelengths. So they have to be really, really huge to be able to basically see much of anything in the sky with any detail. So Arecibo is so large because the wavelengths of light it observes are very long, and to be able to get enough light and high enough resolution, we have to have a really, really big telescope. So speaking of detecting signals, how exactly is it done and what frequency range does Arecibo detect at? Well, first off, radio telescopes are not listening devices. It's a big misconception that when we point a radio telescope towards the sky, we're listening for sounds from outer space. Of course, space is a vacuum, so there is no way to transmit sound. What we're actually picking up is radio frequency light from objects in space. If you take a look at the cartoon on the bottom here, we're showing the whole electromagnetic spectrum, everything from high energy gamma, X-ray, and ultraviolet light to the visible wavelength range that our eyes are sensitive to the longer infrared and radio wavelengths of light. Arecibo detects at about 50 megahertz to about 10 gigahertz, so basically this range represented in green here. And the receiver, what it does is it measures a total voltage that is triggered by the amount of radio frequency light that is detected. It takes that voltage and it turns it into a picture. Basically, we end up with a map of signal strength over a certain region of sky. The stronger the signal, the stronger the voltage, the more radio frequency light we are receiving from that position, and we can convert that information again into a picture. So here on the right, you're seeing an Arecibo image of a galaxy, and if you look closely, you can tell that it's actually a spiral galaxy. There's a bright orange center here, and there's two kind of looping spiral arms around this galaxy. And the images that we get from Arecibo and other radio telescopes are often not as pretty as the Hubble images. Remember, they are often lower resolution, just because, again, we're using very long wavelengths of light. There's not much we can do about that. So when we look at the images, they might look a little blurry or not quite as crisp as some of the pictures we have seen before, but they still contain a ton of information, and they can teach us a lot about stars, galaxies, and even objects in our own solar system. We'll get into all of this in a few minutes when we talk about some of the discoveries that Arecibo has made. Now remember that Arecibo doesn't just receive signals, it can also send or transmit signals that bounce off the ionosphere, or it can send certain frequencies that will go through the ionosphere and travel away into space. To be able to transmit signals, we basically need a device that is really high powered, that can send a lot of radio frequency into space. So to do that, we use devices called klystrons. And these are exactly what TV and radio stations use to generate the signals that they then send through our atmospheres that reach our homes. The one at Arecibo, I think there's actually two of them there, they each generate 500 kilowatts of radio frequency energy into space. They generate and can send that amount into space, which is just a tremendous amount of frequency. That frequency, that light, can then travel outside of the solar system and beyond. We can aim it at solar system objects and look at the reflection back, or again, we can bounce it off the ionosphere if that's what we were interested in studying. The pictures here show, this is a picture of Mike Nolan, the Arecibo director at some point, and then this big red device here is one of the klystrons that would generate the energy. And the little video you see on the right here, this is an asteroid called 3200 Phaethon. Astronomers aimed the radar at this asteroid as it made its close approach to Earth, And then they detected the signals that bounced off the asteroid and came back. And that allowed us to get a sense of exactly what the shape of the asteroid is like. So all of the white signal that you see here is frequency, radio frequency light that has reflected off the asteroid and bounced back. And it allows us to see the shape of the asteroid and also get a sense of its size as well. So having this radar capability is super important for specific types of science, and there are no other radio observatories, even today, that have this capability. So losing Arecibo was a big blow to the astronomers that need to do this type of science, that require that radar to be bounced off of different objects in our solar system to be able to study them. All right, so that is the history and the discussion of how Arecibo works. Let's talk about some of the big discoveries that Arecibo has made over the years. Now, I just picked out a handful of discoveries that I thought were particularly interesting or really, really important to science. And I grouped them together based on topics. So we're going to talk about pulsars for a little bit, then we're going to talk about our solar system, and then we'll talk about a few other things that Arecibo has discovered. So these aren't chronological by any means. They're really grouped more based on topic to hopefully make them a little bit easier to follow along with. So let's start with the discovery of the Crab Nebula pulsar. In 1968, the Arecibo Radio Telescope discovered a pulsar at the center of the supernova remnant we call the Crab Nebula. So let me remind you what a pulsar is, and then we'll talk about why this discovery was so exciting. A pulsar is what's left over after a massive star dies and explodes. It goes supernova, it spits all of its guts into the universe, and the core of the star actually collapses in on itself, and it creates what we call a neutron star. Basically, so much material, usually about 1.5 solar masses or more, is packed into such a small space, something, the size of Earth or often much smaller, sometimes the size of a state or even a city. All of that material is packed in so tightly together that any atoms that existed inside of the core of the star just become neutrons. The protons and electrons combine together, and you ultimately have a ball of neutrons. During that collapse, you have a lot of material collapsing down into a small space, and that often causes the star to rotate, or the core of the star to rotate and spin very rapidly. When a star does that, when it spins very rapidly, it becomes what we call a pulsar. And the name pulsar comes from the fact that this rapidly rotating neutron star will often beam radio frequency light out to ends, and we can detect these radio frequency beams with our radio telescopes. So pulsars are not a new concept for Arecibo. Arecibo was able to detect pulsars, and other radio telescopes were as well. But what Arecibo was able to do for us was actually teach us exactly what pulsars are. The description that I just gave you came after this discovery of the pulsar at the center of the Crab Nebula. You can see the Crab Nebula here. This is the supernova remnant, the leftover plasma of the star that was pushed away into space during the explosion. And finding a pulsar at the center of this nebula meant that the supernova explosion that created the nebula must have also created the pulsar. So up until this point, we did not know that neutron stars and pulsars were basically the same thing. We thought they were two separate objects, and it was unclear exactly how the pulsars were created. But now we know that pulsars are just rapidly rotating neutron stars that beam radio energy out the poles. So this was a really cool discovery that revolutionized our understanding of pulsars and the evolution of massive stars in space. So piggybacking on that, a few years later, in 1974, astronomers Hulse and Taylor discovered the first binary pulsar neutron star system. So in this case, like the cartoon shows on the right, you have a pulsar, a rapidly rotating neutron star that is beaming radio signals out the poles. And this pulsar was orbiting around a second neutron star that didn't quite collapse down enough to actually become a pulsar. These two objects, they orbit around each other, and we would actually expect over time their orbits to decay. The objects should get closer and closer, start orbiting around each other faster and faster, and ultimately collide and coalesce into one object. Now, the reason that we think that these two objects should have a decaying orbit all has to do with Einstein's relativity. Einstein predicts that as two small but massive objects orbit around one another, they should lose some orbital energy in the form of gravitational waves. That's represented by the green squiggle arrows here. These gravitational waves are basically just energy that can kind of ripple through space-time and ultimately travel towards Earth or whatever direction they're aimed at and potentially be detected. So relativity predicts that this should happen, and if we're not able to directly detect the gravitational waves themselves, we should at least be able to see the pulsar's orbit decaying. The pulsar should get closer to the neutron star, start orbiting around faster. And if it does that, then that would be an indirect proof that relativity is correct and that gravitational waves exist. Because if gravitational waves didn't exist, then the pulsar and neutron star should stay in their same orbit. We should see the same period year after year, and nothing would really change. But if gravitational waves do exist and the pulsar loses energy, we should see changes in the rate that we receive the pulsing radio signals. And we should be able to determine that the pulsar is actually getting closer and the orbit is decaying closer to the neutron star. So with this binary pulsar-neutron star system, we're literally able to test Einstein's relativity and indirectly detect gravitational waves. So once Hulse and Taylor found this, they did all of the calculations, they watched the system over many, many years, and what they found is exactly what Einstein predicted. So they literally watched the system over 40 years, and they saw the pulsar decay and orbit closer and closer to the neutron star in a way that exactly matched with its loss of energy through gravitational waves. So the bottom we have the cartoon again, just to remind you what we're looking at. And on the right-hand side, we have a year, so time frame that they measured this, right? They started in the early 70s. They measured it all the way up to 2005. The prediction for the cumulative period shift, or the change in orbital rate of the pulsar, relativity predicts that blue line there. So the mathematical modeling says that's how it should decay and change over time. And the red dots are the actual data points. So the actual data points match pretty much exactly with what Einstein predicted, or relativity predicted. So gravitational waves must exist. This pulsar must be losing energy in the form of gravitational waves, and that must be what's causing this decay in the orbital period. So this was the first indirect proof of gravitational waves, and it wasn't until 2015 that we actually directly detected gravitational waves using LIGO and instruments here on planet Earth. We knew they should be there thanks to this discovery of the pulsar-neutron star binary system, but we just had to take some time and focus on the engineering to be able to actually directly detect them. Now, there was one more big Arecibo discovery that involved pulsars, and that was the very first detection of an exoplanetary system. Remember that exoplanets are planets that orbit around other stars or objects in our night sky that are far outside of our own solar system. And in 1990, Arecibo had detected what we call a millisecond pulsar, meaning that the pulsar rotated multiple times a second. And the pulses ended up fluctuating periodically, which is strange, right? Usually pulsars are very, very consistent. We see the pulse every fraction of a second without fail. But there seemed to be a fluctuation that could be predicted by modeling if there happened to be 3 exoplanets orbiting this pulsar and interacting with it gravitationally. The basic idea is that as these exoplanets orbit the pulsar, they tug on it with their gravity a little bit, and that means the pulsar is going to have a small orbit of its own, and that little motion back and forth, that small orbit of the pulsar, is going to change the rate at which we receive the radio signals, the pulses. So astronomers, when they detected this system, they did some modeling and found that there were 3 planets, 2 of which were a little bit bigger than Earth, probably still rocky planets, but larger than Earth, and 1 really small planet, 0.02 times the mass of Earth, way smaller than most planets and some moons in our solar system. And all 3 of these planets, they happen to orbit very, very close to the star. They had orbital periods of 25, 66, and 98 days, which would put them all about at the orbit of Mercury or closer if they were in our own solar system. So this exoplanet system is very bizarre, in part because of the sizes and distances of the planets, but also because they orbit a pulsar. We wouldn't expect planets to be orbiting a pulsar because the star had died and exploded, and in that explosion we might anticipate it destroying any planets that are in the system. But maybe these planets survived, or maybe these planets formed out of the debris that was left over after the supernova explosion. It's unclear exactly how these exoplanets got there, but they're definitely the first distinct detection of an exoplanet system ever, and a very unique one at that. So speaking of planets, let's come back to our own solar system and talk about some of the big discoveries that were made by bouncing radar signals off of planets, asteroids, and other objects in our own solar system. One of the first big discoveries that was made involved the planet Mercury. So here we have a cartoon showing the orbit of Mercury around the sun. Mercury orbits the sun in about 88 days. Here's Earth's orbit around the sun. Of course, it takes about 365 days for Earth to go around the sun. The closer you are to the sun, the faster you're going to orbit. And the closer you are to a star, the higher the probability that the planet is going to be what we call tidally locked. Tidally locked would mean that its rotation rate, one day, is equal to the time it takes for it to go around the sun, which is 1 year. So early on, like hundreds of years ago, we were able to predict Mercury's orbital time, right? To figure out the 88 days, that's easy based on Mercury's motion in our own sky. And because Mercury is so close to the sun, it was long thought that it was tidally locked, that one day would be 88 days. But once we started to have observatories that could study the planets a little bit closer, we looked at Mercury and made some very rough temperature maps. And the temperature maps, like the one shown here from the VLA, the Very Large Array, actually show that the temperature on Mercury is pretty uniform. And that's not what we would expect from a tidally locked planet. If the rotation rate is equal to the orbital rate, that means that the same side of Mercury would always face the sun, and the opposite side would always face away from the sun. That would mean that the side closer to the sun would be really, really hot, and the side opposite the sun would be really, really cold. But in this rough temperature map here, red is hot and blue is cold. You see that, one side of Mercury is red and yellow, but the other side is relatively warm as well. It's not perfectly uniform, but it generally has a similar temperature scale. Definitely not super hot on one side and super cold on the other like we expected. So this kind of hinted to astronomers that maybe Mercury wasn't tidally locked. Maybe it rotated in a slightly different way. By bouncing radar off of Mercury using Arecibo, they were actually able to determine, back in 1965, that the rotation rate of Mercury was only 59 days. So using the same technique that we talked about for studying the ionosphere, if you bounce radio signals off the side of Mercury that's rotating towards you versus the side that's rotating away from you, you're going to see a slight Doppler shift in frequency, and the width of that frequency range will tell you something about how quickly the planet is rotating. So on the right-hand side, you have two measurements from the original 1965 paper. This was March of 1965. This was August of 65. This is basically the frequency change, the Doppler shift. And then this is over time. So they watched it over, roughly a month's time in each case. And you can see some dashed lines here. This is the predicted data set at 59 days rotation, 88 days rotation on the bottom. Same here, 59 days, 88 days. And what you can see is that the data points much more closely match the 59-day prediction, and there's literally like no data down here at the tidally locked 88-day rotation. So what does that actually mean? Well, it means that Mercury orbits once, 1.5 times every time it goes around the sun. So for every year, every orbit around the sun, it rotates on its axis 1.5 times. So if we look at the little cartoon that popped up, we start over here and imagine that you are standing at the pink arrow. We have counterclockwise rotation of Mercury. After 15 days, you've rotated a quarter of the way. 30 days, half of the way. 44 days, 3/4 of the way. And by day 59, one full rotation, your pink arrow is pointed directly towards the left again. So you can watch that continue, right? We can go through the cycle. And once we get back here, we jump to year 2, and we watch Mercury orbit around, and we could, project the rotation rate as far into the future as we wanted to. But this was really great because, we're learning something simple, but something very important about planets in our solar system that we would not have been able to learn in any other way, especially back in 1965. Now, Mercury wasn't the only planet that we studied with Arecibo. We also studied Venus as well. In the 1970s, we did the same thing. We bounced some radar signals off of Venus, and they did it for two reasons. One, to figure out the rotation rate. Turns out it's 245 days in the opposite direction, or what we call retrograde, so it rotates on its axis clockwise. But we also had the ability, if we sent the right frequencies, to pierce through the clouds of Venus and actually get a sense of what the surface looks like without actually having to travel there. So on the right, you have an image from Mariner 10. This is actually a later image from 1974, but it's here just to show you that Venus is covered in clouds. There's a very thick carbon dioxide cloud layer around Venus. And by sending the right frequency signals from Arecibo towards Venus, we could go through the clouds, bounce them off the surface, and get our first view of what the surface of Venus actually looks like. Now, it's not great, it's not super high resolution, but what you can see here is stronger signals in some areas, that would be the lighter regions, and weaker signals in other areas. And that basically gives us a sense that the surface of Venus is not uniform, right? We're not really able to tease out too much of the distinct structure, but we are able to get a sense that there might be some craters or some pits. We now know that a lot of this is due to lava flows on Venus. But again, we just started to get a sense of what it looked like and that it had some structure to it. As the years went by, astronomers were actually able to make some big upgrades to the Arecibo Observatory, along with the receivers and transmitters, and we were able to get some really crisp images. This is a 2015 image of the northern hemisphere of Venus, and look at that detail. Very high resolution imagery here. We can see that there are not too many craters. A lot of the holes and the bumps that you see are actually caused by lava flows. So just like we see Mare on the moon, where lava has flown and kind of created a dried up lake looking feature, that's what we see a lot of here on Venus. So this helped us learn more about the structure and the surface of Venus, gave us some clues as to how hot the surface must be, and also told us that it must have been volcanically active at some point in the past. Not only can we study planets using the radar from Arecibo, we can also study asteroids. Arecibo has created models and maps of a variety of different asteroids, and I just picked this one as an example because it looks the coolest. This is 216 Cleopatra, and it kind of looks like a dog bone. So here we have radar imagery of Cleopatra from different angles. So the asteroid, which exists in the asteroid belt, is orbiting the sun and it's also rotating. So we can see it at different angles at different times. And we're therefore able to basically get a 3D map of what the asteroid looks like. So it turns out the asteroid is about 171 miles from end to end. It has this double-lobed shape that kind of looks like a dog bone. Unclear if this is because of like the evolution of the asteroid. So did it basically weather and create the structure? Was it hit by objects that kind of, knocked out some of the central material? Or was it two asteroids that collided and stuck together at some point in the past, creating this structure? We don't really know for sure, but it's definitely an interesting looking asteroid. And with other radio telescopes and other modern day telescopes, we were actually able to learn that this asteroid has two moons with it as well. So here is a little picture on the bottom left there. This is from the VLT, the Very Large Telescope. This is an optical telescope on the ground. You can see the asteroid, not quite in as much detail, but you can still see the double lobe structure. And these two dots on either side are actually moons, tiny moons that orbit around the asteroid. And we know they're moons because we were able to image it over time, and we actually saw them move around the asteroid and with the asteroid as it orbited around the sun. So asteroid mapping and asteroid detection, especially the asteroids that get close to Earth, were a huge thing that Arecibo was focused on for many, many years. The last thing I want to talk about briefly is actually not a discovery, but rather a cool thing that Arecibo did. And if you've heard me talk about, life in the universe before, you've probably heard me mention the Arecibo alien message. So in 1974, astronomers Frank Drake, Carl Sagan, and a bunch of others got together and came up with some information, a message that they wanted to send to potential alien civilizations that described us humans and planet Earth. They chose to send this message using the Arecibo radar into space in the direction of this globular star cluster called M13. Now, M13 is pretty far away, 25,000 light years away, but they chose this object because it was so dense, because there's a lot of stars there. And they figured more stars, higher probability of having a planet with alien life on it. So the Arecibo message looked like this, the picture on the right there. The left-hand side is a pictorial version of all the information. The right-hand side is exactly what it says. So on the top, you have the numbers 1 to 10. This purple thing is representing the elements that are important for life. The green is nucleotides, the building blocks that make up our DNA. Information about the number of people on our planet, the height of an average human being, our solar system, with Earth being risen to show that we are the third rock from the sun, and then some information about the radio telescope in case they wanted to beam a message back. So this was sent into space. We have not received a return signal yet, but if it's 25,000 light years away, it's going to take 25,000 light years for the information to get there, 25,000 light years to come back. So we don't really expect to hear back from the aliens for another 50,000 years. So unfortunately, we've got some time to wait. All right, so let's finish up by talking about the end of Arecibo. What ultimately caused the telescope to crumble and collapse in 2020? Well, during its heyday in the 60s, 70s, 80s, and 90s, Arecibo was operated by Cornell, fully funded by the NSF and NASA, and heavily used by astronomers. But by 2011, the usage of Arecibo started to dwindle a little bit, and control of the telescope was transferred over to SRI International, which is a nonprofit organized by Stanford, which supports research and development in a variety of fields. It's not necessarily astronomy specific. This organization became the site operators, and NASA provided some funding at this time to study near-Earth asteroids, but other than that, there was not a lot of funding to operate the telescope and do much science. In 2017, there were a couple big hurricanes, Hurricane Irma and Hurricane Maria. They caused some damage to the telescope, not detrimental damage, but some line feeds were damaged, a little bit of dish damage, but nothing that couldn't easily be repaired. But of course, repair costs money, right? So in 2018, the University of Central Florida actually stepped up and said, you know what? We have some scientists that want to use this telescope. We have some funding. We'll take over the operations and we'll help cover the repair cost to repair Arecibo from the hurricane damage. So as that started to move forward, some bad things happened as they were attempting to repair the telescope. In August of 2020, one of the newer auxiliary cables that is used to hold up the receiver in the Gregorian dome here ended up slipping out of its socket, and it fell down from the tower and ultimately crashed into the dish. You can see in the images here, there's a big hole in the dish on the left, and here's a zoom in of it on the right there. So a lot of those aluminum panels in the dish were damaged. Why did this happen? Unclear. The cable should not have slipped out of its socket, so they're thinking maybe bad socket construction, but it's really kind of hard to tell exactly why it failed. Now, the damage that it caused was not irreparable, but in November of 2020, unfortunately, a second cable snapped, and it caused even more damage to the dish. More aluminum panels were damaged. This cable ended up just literally snapping and breaking, and it was only experiencing 62% of its maximum load. These cables were designed to hold at least twice the maximum load that they would ever have to carry, but this one broke at a much lower level. So what they're thinking is that maybe degradation from salt water on the cable over the 50 years that Arecibo was functional, that may have caused the cable to become weak, ultimately snap, and again, fall and damage the dish. So both of these things were really bad, but again, not irreparable. They could be fixed. So scientists got together with engineers and said, you know, how do we fix this? What can we do to fix the telescope? And the engineers said, it can be fixed, but it's very, very dangerous. And the scientists and the leaders of Arecibo could not find an engineering company willing to take the human risk to get up there and repair the telescope, because they were afraid that the Gregorian dome and the receiver would ultimately collapse because of more cables breaking. It was hard to tell if any other cables were on the verge of snapping. So the engineers sadly suggested that there would be a controlled demolition of the telescope. But before they could plan any of this, on December 1st of 2020, a third cable snapped, and this cable caused the receiver to fall to the ground. So in the images that you see in the bottom here, this is the Arecibo dish. This was the receiver, and this huge destruction here is the receiver and all of the cables crashing through the bottom of the dish. And on the right-hand side, this is a view from basically inside that hole, from underneath here, and you can see just how much damage had happened. So at this point, now the telescope is not able to be repaired, definitely not safe to get up there and fix anything anymore. So ultimately, it was decided that Arecibo would just be taken down. So before we talk about what's next, I want to show you this amazing drone video of the collapse of Arecibo. It was purely by chance that some engineers happened to be flying a drone up to check out the cables and try and assess the damage when those cables snapped, ultimately dropping the dome and the receiver onto the dish. So what you'll see in this 2-minute video here, first they show you a view from a stationary camera on top of one of the towers, And then they show you the drone video where it actually watches the cable snap and then it turns to see the dish or the dome fall onto the dish. So really sad, but really amazing that we have this video to see. So let me play it for you here. So there you can see the Gregorian dome falling to the ground, portion of the tower falling with it. And then next up here will be the actual drone footage. So you can see there's wear and tear on the cable already. It starts to snap. And the whole thing comes crashing down. Gosh, just so unfortunate. So sad to see it go down that way. So the NSF is continuing some funding to clean up the site, right? Everything has to be disassembled so that it's safe to be in that area again. And the estimated cost of all of this is something like $50 million to clean up this damage from Arecibo. So what's next, right? With Arecibo gone, what do we have to look forward to in the field of radio astronomy? Well, the NSF and other organizations are discussing a possible replacement for Arecibo. No big plans as of yet, but they're definitely thinking about building something similar. We also have a lot of other radio telescopes and radio dishes. We have ALMA, the Atacama Large Millimeter Array. We have the VLA, the Very Large Array, and others that are interferometric radio observatories, where we have multiple smaller dishes whose information and signals can be combined to act as if they are one humongous radio dish. That gives us really high resolution and very, very detailed images of outer space. So a lot of science is going to be done with those telescopes. And we mentioned in the very beginning that China has recently built a massive new telescope. You can see it here. This is a picture of FAST, the 500-meter or roughly 1,600-foot radio dish. It is similar to Arecibo in that it is a single solid radio dish with a receiver at the top, but it does not have beaming or transmitting capabilities. So it's only going to be able to receive signals from space. So we'll have to wait and see what information China is able to get from this telescope. Scientists across the world are collaborating with China as much as possible so that we can all use it and all benefit from this amazing piece of equipment. But even with FAST existing, I still think there is a benefit to rebuilding Arecibo in some way or another. So I look forward to hearing what the NSF comes up with, and hopefully we'll have a brand new telescope to think about in the near future. So thanks for joining me today. I hope you enjoyed learning all about the Arecibo Radio Telescope, and I look forward to seeing you at the next lecture.